It's a nototheniod, one of a group of fishes that have evolved a whole bag of tricks for surviving in super cold temperatures, only one of which is their biochemical antifreeze. And they need them because it is cold. The Southern Ocean isn't totally frozen over, but it is covered by sea ice for much of the year. In the coldest waters near the coastline, ice crystals form in the water column and mats of ice blanket the ocean floor. For the fish, there's nowhere to hide. At the risk of stating the obvious, freezing is really bad for most living things. Ice crystals are sharp, and as they form and expand, they can lead to serious tissue damage by basically causing cells to burst and die. But these Antarctic fish are cool with it. They're often found alive and happy, hiding and looking for food right there in the ice. Having ice outside is one thing, but their insides are full of tiny ice crystals too, swallowed from the seawater. And while the freezing point of seawater is minus 1.9 degrees Celsius, the freezing point of the fluid inside a fish's body is in the neighborhood of a degree warmer. That's because the amount of stuff dissolved in water lowers its freezing point, which in chemistry we call freezing point depression. Dissolved salts, like what's in the ocean, are quite effective at lowering the freezing point of water. But fish are only about 1/2 as salty as the sea, so they risk freezing in places where the seawater gets cold enough to freeze. So once that ice gets into the fish, it should freeze from the inside out. Normal freezing point depression isn't enough here. That's where the antifreeze comes in. Specifically, these fish have antifreeze proteins in their bodies. The proteins glom onto the surface of invading ice crystals, completely covering them. Researchers believe the protein actually fits in with the structure of the ice crystals, so that it can bind to them in place of more water molecules and prevent the ice crystals from growing any bigger. Then, the ice crystals hang out in microscopic form in the fish's body, and eventually end up in its spleen, unable to grow bigger and cause the fish any major harm. This antifreeze action is so powerful, it effectively creates a gap in the freezing point of the fish's body fluids between where they should freeze and where they actually do. They lower the fish's internal freezing point by more than a degree Celsius to as low as minus 2.7. Since the seawater can't get much colder than its freezing point of minus 1.9, the fish literally can't freeze. Antifreeze proteins aren't unique to Antarctic fish either. Fish like these, and even some insects, have evolved their own varieties of antifreeze proteins. But while they explain how fish can survive in far-off cold oceans, antifreeze proteins might be closer to home than you realize. Research is looking for ways to leverage these natural antifreezes to preserve other types of biological material than the fish that evolved them, like keeping organs for transplants at lower temperatures so they can last longer without being damaged by ice. But that's still a work in progress. The fish, meanwhile, have managed to use some very clever biochemistry developed over millions of years of evolution to survive one of the harshest habitats on Earth.